Hello everyone and welcome to the next video in the series. This video is a technical skills video on the topic of the structure of decimals. To begin, let's take a look at some examples of decimals. Numbers such as 42.8. Decimals could of course be negative, such as negative 0.023. A number such as 14 could be thought of as a decimal number without a fractional part. And same thing with negative 280. Now you might wonder whether we can call 14 and negative 280, whether we can refer to them as decimals, because for one thing we called them natural numbers and integers earlier with formal notation, and also there is no decimal point really, or at least we haven't written it down, so whether they can be considered to be decimals or not is the question. And the answer is it depends on your point of view. If you're thinking formal notation, so as in theoretical discussions in the sciences, then yes, of course you can think of 14 and negative 280 as natural numbers and integers. But if you're thinking base 10 notations, such as decimals, as would be the case if you're working on applications of theoretical science or scientific theories, then you can think of 14 and negative 280 as decimal numbers with no fractional part. And of course we have 0 as an example of a decimal number. Now, terminology, there are 4 phrases that I will be using throughout the videos that will follow on decimals, and these are the whole part, the fractional part, the decimal point, and decimal digits. So let me begin by showing you a diagram. On the right side, the whole part refers to the left side of the decimal point, so where you see the digits 7, 1, and 5. Altogether, we refer to this as the whole part. Next, we have the fractional part, and these are what you see on the right side of the decimal point. So the digits 2 and 9 taken together, we refer to the whole thing on the right side as the fractional part. Now, the terminology comes from the fact that, or the agreement at least, the way we have set up decimals, that's the way they work, is that on the left side of the decimal point, no matter what you write, it always refers to how many whole things you have. So 715, if you are talking about pies, then we are talking about 715 whole pies. And on the right side, as we will see later, no matter how many digits you have and no matter what digits you have, the sum total of those will never add up to even one whole pie. And therefore that's why it's always a fraction of a pie. That's why we refer to it as a fraction, as the fractional part of the decimal number. The point itself is called the decimal point. And another phrase that we use quite frequently actually is the phrase decimal digits. And by this we mean digits on the right side of the decimal point. So 2 is a decimal digit and 9 is a decimal digit. We can say that this number has 2 decimal digits, and those being 2 and 9. We use this in a number of places. As an example, one is where we say, for example, round the answer to 1 decimal digit. And that means show a digit here, round it to this place. 1 digit on the right side of the decimal point. All right. So following the terminology, and actually let me give you 2 more examples here, just to be clear about, make sure that just to make sure that we have an understanding of how the terminology works. In 5.3, 5 is the whole part, 3 is the fractional part. We have the decimal point, and there is 1 decimal digit. That digit is 3. 2.69, the whole part is 2, the fractional part is 69, which in fact it is 69 hundredths, and also 3 is 3 tenths, and we'll come to that once we talk about place values. So the fractional part is the 69, there is the decimal point, and there are 2 decimal digits. Those are the digits 6 and 9. All right, next we have place values, and we are talking here about tenths, hundredths, thousandths, 10,000s, and so on. And you notice the difference between these words and also the words that we used to talk about place values in natural numbers is that these ones end in th. So we are talking about a tenth and not a 10. We are talking about a hundredth and not a hundred. And here are the place values. So now here's the decimal point. On the left side of the decimal point, which is the whole site, we have the same place values as we had with natural numbers. So we have the ones and then followed by tens, hundreds, thousands, and so on. On the right side, and this is where the decimal notation extends the structure that was introduced with natural numbers. In the sense that if you take a look at the natural number site or the whole site here, what we have is place values which are, each of them is 10 times larger than the one on its right and 10 times smaller than the one on its left. So if you think of 100, for example, 100 is 10 times larger than a 10, and it is also true that 100 is 10 times smaller than 1,000. And if you take a look at tens and ones, same relationship. A 10 is 10 times larger than a 1, and a 1 is 10 times smaller than a 10. And that same kind of subdivision continues across the decimal point and down the stream. So for example, if I compare the size of a 1 here and the size of a 1 here, a 1 here is 10 times larger than a tenth, and a tenth here would be 10 times smaller than a 1. Okay, now comes a concept, place value size relationships. And this concept is pretty important. In fact, it sort of is the base upon which all of the concepts that have to do with decimals, as well as algorithms that we use to add, subtract, multiply, divide, and so on to work with decimals, they're all based on this particular understanding of place value size relationships. So this is a topic you should pay close attention to. And as I said, the topic is used, or the concept is used, to justify both the introduction of new concepts with decimals, as well as the algorithms that we use as examples of those in making sense of decimal digits, which are the digits on the right side of the decimal point, as I introduced earlier in this video. In ordering decimals, again, place value size relationships become important in understanding how we order decimals. In rounding decimals, we use them to explain why we ask for a certain number of significant digits. This is a topic I will actually discuss in just a couple of minutes. The place value size relationships are used to explain the reason the algorithms for addition, subtraction, and so on work, and also in graphing decimals. So it's a pretty important concept. And this concept is what I just alluded to, that each place value is 10 times smaller than the one on its left and 10 times larger than the one on its right. Now, to give you a visual feel for what this means, let's take a look at the diagram on the right side here. And here we have the size of a 1, which goes from the left end over here all the way to the right end over here. So that's a 1. And if we take this and divide this into 10 parts, we get the diagram that we have down here. And the size of one of these pieces is shown by a 1 on the right side of the decimal point. So in fact, let me actually try to write these down for you. So if you have a 1, I'm going to type the numbers down here. So we have a 1 and then decimal point, and then we have 1 and followed by another 1. The one that you see here on the left side of the decimal point refers to a size that's this long, a length that's this long. Whereas a 1 on the right side of the decimal point refers to a length that's only this long. So you can see that a 1 here has a length that's 10 times smaller than the length of a 1 over here, which has that kind of a length. And if we take a 1 here, one of these pieces, which is represented by a 1 here, and if we divide that into 10 parts, we end up with one of these tiny pieces over here, and the size of that is given by the 1 here. So you can see how the size of a 1 changes depending on where it is. If you have a 1 here, you're talking about this size. If you have a 1 here, you're talking about 1/10 of that size, which is this much. And if you're talking about a 1 here, you're talking about 1/10 of this size. This distance is divided into 10 parts, and then one of them becomes this one. And you can see for, one of the things that this means is that the sizes become really small very quickly as you go downstream in a decimal number. If I can add one more 1 to the number that we have here, so let me put another 1. If you think of this one being the size of a small piece over here, and now you take that and divide that into 10 parts, and the size of one of the tiny parts that you get would be represented by that one. So you can see going 3 place values down from this one, down 1 place value, 2 place values, 3 place values. The size goes from a size that is this long to a size that is 1/10 of one of those tiny pieces here, which is this one. And this explains the point I was trying to make here, that if you understand place value size relationships, it explains why let's say in your science courses, in your chemistry courses or physics courses, they usually say round the result to let's say somewhere between 3 to 5 significant digits, and that's because when you talk about now, I know I haven't talked about significant digits yet, but you can, for now, just very loosely, you can think of them as being the digits that you have when you measure something. If you're measuring something, let's say the length of a beam or some fence, then writing down 1.111, that's pretty good enough, because if you think about it, we're talking about a fence that has a length represented by this one, which is that long, and on top of that there is an additional part that's represented by this one, which is that long. So in total now we have a fence that's whose length is the sum of this piece and this piece. And on top of that, there is a bit more represented by this one, which is the size of this tiny piece. And I think by the time we get to this other one, which is 1/10 of one of these tiny pieces, then we would probably say, that's accurate enough. And this is 4 significant digits. So if you have 5 of them, that's way too accurate. And for these reasons, often in your science courses, they ask you to round the result to 3 to 5 significant digits. Now 2 significant digits would be a bit rough. We might know that the length is equal to this one and this one, but we may also want to know how many of these ones we have, because if you have one of it, it may not matter so much, but if you have, let's say, a 4 here, then that would mean 4 of those, and that might be long enough for us to take into consideration. So 3 significant digits are pretty good, 2 is rough, and 5 is pretty accurate, way pretty accurate, and anything beyond 5 is somewhat unreasonably accurate, at least for everyday life problems and problems when you deal with problems in basic sciences. Okay, the last topic for this video, and by the way, before I go, let me show you another image that shows this the relative sizes of a 1 here and the 1 over here. In a sort of like a zoomed in kind of a diagram. So again, you can see that if you take 1/10, which is this long, represented by a 1 over here on the right side of the decimal point, and you divide that into 10 parts, you end up with a size which is about this big, and one of these is represented by a 1 here. That's the size of a 1/10 compared to the size of a 100th. And in case you're trying to relate the sizes of place values that are not adjacent to each other, such as hundreds and tenths, Then of course, because one of these is equal to 10 of those, and one of these is 10 of these ones, and one of these ones is equal to 10 of those, then you can say that 100 is 1000 times larger than a tenth. A quick way to work it out is to put a 1 where the larger place value is, and then fill up with zeros until you get to the smaller place value, and that will tell you how many of the small ones fit into a large one. So in this case, 1000 tenths make 100, and vice versa. You can say, or if you look at it the other way, you can say that 100 is 1000 times larger than a tenth. Alright, so now next we would like to talk about interpretation of decimal digits. And this is the last topic for this video, and it's actually a very important topic as well. This is something that you should be able to do. Anyone who claims that they understand decimals should be able to make sense of decimals in two different ways. And this is making sense of them one digit at a time or all together. Just a reminder that decimal digits are digits on the right side of the decimal point. So on the right side, you should be able to make sense of the digits one at a time or all together. And this is how you can do that. I'll give you an example of what I'm talking about here. Let's say we have 0.23, and this can be interpreted as either 2 tenths, 2 is in the tenths place, and an additional 300ths, so as 2 tenths plus, now that should have been a 3, let me change that so there is no confusion here. There we go. So we have 2 tenths, and then we have 300ths. So we're talking about the totality that we get when we add 2 tenths and 300ths. So here we are making sense of the digits one at a time. How many tenths we have and how many hundredths we have. Or you can make sense of them all together. And you can think of this as 23 hundredths, which you can write down as 23 hundredths. In fact, if we were going to add 2 tenths and 3 hundredths, you would eventually come to 23 hundredths. Now, to give you an idea as to what this means, if you take a look at the diagram on the right side, the top is where we are seeing each of these digits as separate from the other. So we are making sense of the digits one at a time. We're talking about 2 tenths, so 2 is in the tenths. We're talking about 2 tenths, so we are talking about a piece, pieces that are this long, 2 pieces, each one is this long. So we're talking about 1 tenth, and then 2 tenths. And then we make sense of 3 as how many hundredths we have. And so in addition to 2 tenths, we have an additional 3 hundredths. And so this is how we see it, as 2 tenths plus 3 hundredths. And now the second interpretation, which is 23 hundredths, of course if we divide a tenth into 10 parts, we get a hundredth, and because we have 2 tenths, we end up with 20 hundredths. As you can see here, we have 10 hundredths and another 10 hundredths for a total of 20 hundredths, and then we have another 3 hundredths. So we can see this as 23 hundredths. In total, we have 23 pieces. Each one is a hundredth. So once again, with 0.23, we can see this as 2 tenths, which is 2 pieces that are this long, and then an additional 3 hundredths, which is the rest of it, which brings us to here. Or we can see it as 23 hundredths, which is how many of these small divisions we have. We have 23. Okay everyone, this brings us to the end of this video, and in the next one I will be taking up the topic of the formal reading of decimals. And I will be gone for now in 3, 2, and 1.